Hi friends, today we'll be presenting our project Deep Learning and Deep Reinforcement Learning for Self-Driving Cars. As of today, the entire world is running behind developing technology that would make self-driving cars a reality. The first attempts made at autonomous vehicles focused on creating assisted driving technologies. The Advanced Driver Assistance Systems or the ADAS systems consist of operations like emergency braking, backup cameras, adaptive cruise control, self-parking systems, etc. These were features that were initially available only in luxury vehicles. But now, at least some of these features are being provided in every vehicle. As technology evolved over the recent times, more and more people started working on the self-driving car technology, aiming at complete autonomy, thus making this a race to the top. The technologies being heavily researched on and currently being used in these cars are computer vision, deep learning, motion planning, sensor fusion, controls, localization, and mapping, to name a few. It is a known fact that the problem of self driving cannot be tackled using just one of the above mentioned technologies, and that it has to be an hybrid approach. However, the technology that is really driving all these advancements is deep learning. Deep learning has evolved tremendously over the last few years, the major reasons being the ability to perform high level of computations due to the advancements in the GPU technology and the availability of large amounts of data. Similar advancements have happened in the field of reinforcement learning in the recent times. Although reinforcement learning has been around since a long time, it wasn't as popular in the machine learning community as it is today. The most significant advancement was made when DeepMind introduced the DeepQ network algorithm. They tested DQN on many Atari video games using unprocessed pixels as input and found that it is capable of human level performance. They used a deep neural network as a function approximator to estimate the action value function used in the Q-learning algorithm. This was the first instance where reinforcement learning was coupled with deep learning, leading to the creation of deep reinforcement learning. We strongly believe that deep learning and reinforcement learning, along with other technologies, will bring autonomous cars to the masses. This is because with a pure deep learning approach, although the neural network will be able to memorize things and give you excellent results in terms of perception, detection, and recognition, it will never become good at reasoning. Consider scenarios like a deer jumps out in front of the car. The car should slam on the brakes. A car is slowing down up ahead. The car should change the lanes. For autonomous vehicles, these decisions aren't so easy. Rather than programming cars to anticipate every scenario, we can program cars to learn to how to navigate scenarios on their own. A deep reinforcement learning approach will essentially train autonomous vehicles by rewarding good and punishing bad actions. In this work, we work with both deep learning and deep reinforcement learning approaches to teach the car or the agent to drive from a start to a goal location using human driven data for the deep learning approach and its own experiences for the deep reinforcement learning approach. After experimenting and not crashing, the car will learn what to do in a variety of situations and will be able to apply that to future scenarios. This work is done entirely in simulation as we cannot afford to have a car actually crashing into people and or objects and learning from real life experiences. We feel that the incorporation of reinforcement learning based approaches, especially in the field of autonomous cars, would require a lot of research in simulation before anything can be tested on an actual car. Our problem statement was using techniques of deep learning and deep reinforcement learning to simulate autonomous driving using ROS and Gazebo simulation environments. The problem we focused on was divided into two parts: the environment and learning how to drive. Before we could start with the actual reinforcement learning task or the deep learning task, we first needed an environment for the car to traverse in. Recently, the Open Source Robotics Foundation launched the simulation of a Prius car using ROS Kinetic and Gazebo 8. The vehicle's throttle, brake, steering, and transmission are controlled by publishing to ROS topics. All the sensor data is being published using ROS and can be visualized with RViz. We use these tools as no one has used this environment so far for teaching a car to drive using deep learning and deep reinforcement learning. Once we had the environment set up and ready to use, we needed to focus on the learning to drive part. This part consisted of multiple steps, the first and foremost being able to control the car by publishing messages over ROS topics. After that, we explored various algorithms that could be used to train the car to learn to drive. We set a start and a goal location to be able to make it traverse from the start to goal location in the shortest time, with no traffic or obstacles. So now let me give you a brief overview of our project. As mentioned earlier, we worked with both deep learning and reinforcement learning to solve the problem of autonomous driving in simulation using ROS and Gazebo. The deep learning approach involved collecting human-driven data by driving the car around in the real world and recording the camera images and the steering angle values in a ROSBag file. This data was then extracted and used to train a convolutional neural network for behavioral cloning. Behavioral cloning is basically the task of imitating or mimicking the human driving pattern. The car learns the next action based on the human driving data that it saw during training. Although this looks like a quick and easy approach, it might fail or give undesired performance when the car comes across scenarios that it has never seen before. It does not have any intuition of the probable best action that it could take in such scenarios. Its decisions mainly rely on the data that it sees while training. If the training data is that of a bad driver, then it is very likely that a trained car will also drive poorly. Thus, the need of reinforcement learning. The reinforcement learning approach makes the car use its own experiences collected by the car during training by constantly exploring and exploiting states. Exploring is basically when the car takes random actions in order to visit states that it has not visited in the past. And exploiting is when the car visits those states again and again that have proved to achieve maximum rewards in the past. Thus, reinforcement learning for a problem like ours that involves an infinite state space requires creating a perfect balance between exploring and exploiting in order to converge to the desired behavior. We make use of the Q-learning algorithm and use a deep neural network as a function approximator to approximate the Q values, thus making this a deep reinforcement learning problem. This approach is more intuitive and it is not dependent on human-driven driving data. The performance is more dependent on the car's own experiences and the balance created between exploration and exploitation. Now let's discuss the environment worlds. For the environment, as already mentioned, we use the Gazebo simulator interfaced with ROS for getting the state of the world, the state of the car, etc. via ROS topics. We had ROS topics that were publishing the current steering angle and the world pose of the car respectively. The car has also been mounted with a bunch of sensors like cameras, LiDARs, and sonars, whose data is also being published on ROS topics. Essentially, this data is required for training. The car could also be controlled by publishing on the ROS topic steering command. We are considering four environments. The raceway world, which is simulating the Sonoma Raceway track in California. The dirt track world, which is simulating a simple loop track which is shaped as an op-round with no pedestrians or vehicles. The M-City world, which is simulating the M-City world of the Georgia Tech University, built for testing autonomous cars. The City Sim world, simulating an urban environment with pedestrians, vehicles, etc. Having the city worlds can help to take this problem further to proceed with city-like environments with pedestrians and other vehicles. One problem that was faced by us was the real-time factor in the Gazebo simulator. For example, Because of many objects in the world, like sidewalks, moving cars, pedestrians, etc., we faced such an issue in the city sim world where the real time factor was reduced to 0.25. This can hinder the process of training, and therefore we made use of the raceway and dirt track for the deep learning and the deep reinforcement learning approaches, respectively. This slide shows the images of the raceway world, the city sim world, and the dirt track world. A very important part of the environment setup was defining episodes for the deep reinforcement learning problem. Most reinforcement learning problems can be broken down into sequences in which an agent interacts with its environment until it reaches a certain terminal state that initiates a reset to its initial state. Each subsequence of agent-environment interactions between initial and terminal states is called an episode. For each episode, the car has been programmed to always spawn from the exact same initial position or the starting position. Similarly, a terminal or goal location is defined which would mark the end of an episode as the car completes the task of going from the start location to the goal location. In order to decide when an episode should terminate, we added two conditions. The episode would be considered to be terminated if the car reaches the goal location or the number of time steps exceed a certain threshold. Another important part of the environment setup was defining a reward scheme. Let me explain. For the deep learning approach, we can probably use any of the worlds discussed earlier, as the only requirement for that approach is recording data by manually driving around in the selected world and using this data to train our deep neural network. However, for the deep reinforcement learning approach, we need to select the world very carefully, as we will have to define a reward scheme accordingly that would be used by the car to learn to drive. An incorrect or inefficient reward scheme would result in undesired driving behavior. The OpenAI Gym library gives us access to a standardized set of environments and can be used for developing and comparing reinforcement learning algorithms. This library handles the environment part of the problem, including the reward scheme for each environment, thus allowing the user to concentrate only on the algorithm part. But in our case, since the environment also needs to be handled by us, the problem becomes more complex and we need to define a custom reward scheme. We had to be very careful while selecting the word we want to use for the deep reinforcement learning approach. Since this approach is more complex compared to the deep learning approach, we decided to select a world with minimum complexities with no traffic and no pedestrians. We chose the dirt track as it is a fairly simple world, and also defining the reward scheme for this world is easier compared to the other worlds mentioned. As seen in the figure on the left, we align the dirt track in Gazebo in such a way that the center of the track coincides with the origin of the world coordinate system. As it can be seen from the figure, the world being used has the shape of an orb round, which is basically a rectangle with a semicircle at each horizontal end. We made use of objects in Gazebo to get the world coordinates of the track at various points as shown in the figure on the left. These points denote the total track area that is available for the car to drive. In order to define the reward scheme, we select the center part of the track to have positive reward and the left and right parts of the track to have negative rewards, as we want the car to be driving in the middle of the track at any given time. This would ideally force the car to drive in the center of the lane in order to gain maximum reward. This can be clearly seen in the figure on the right. The position of the car with respect to the world coordinate frame is constantly being published on a ROS topic called getPose. Thus, we use this to check whether the car is located in the center of the lane or the side of the lane and then assign a positive or negative reward for each action accordingly. Now let's dive into the methodology. To learn how to drive the car, we use two methods: behavioral cloning using deep learning and learning from own experiences using deep reinforcement learning. Now we'll see each of these methods in detail. In this part, we use deep learning to teach the car how to mimic the human driving pattern. It has three major portions involved: data collection, model and training, and testing on the track. Now let's see each one of those in detail. In this part, I'll explain how the data was collected for training. So first we chose the Sonoma Raceway track for this problem. Out of all the environments, there were two main reasons why we had chosen the Sonoma Raceway track. Firstly, it was suitable for collecting data as we got a really good real-time factor in this gazebo world, so collecting data while manually driving was smoothly done. Secondly, it provides a closed loop with clearly marked boundaries, which were necessary for the model. We captured data from the three front-facing cameras that were mounted on the car. Having three cameras gave us a wider angle view of the road and hence captured the road and the turns very well. The steering angle of the left and right cameras was shifted by an offset to simulate conditions where the car tries to come back to the center of the lane. Having three cameras also provided three times data when compared to a single camera data collection. The three images from the car were matched for the timestamp along with the corresponding steering angle. The ROSBAG files were recorded by driving the car manually for 5 to 6 times using a joystick or a keyboard. The BAG files were then extracted to generate the images into three different folders and a CSV file that mapped the images to the steering angle. Now let's dive into the model and the training part. Since this problem involved predicting the steering angle value, which is a continuous value, the problem was a regression problem. The model that we used was inspired from NVIDIA's paper on end-to-end learning for self-driving cars. As it can be seen in the image, the model has 5 convolutional layers and 3 fully connected layers. The images were pre-processed before feeding them into the network. We applied operations like cropping, resizing, flipping, and randomly applying brightness. The figure on the left is that of an original image, and the three images on the right show the cropped and resized image, a flipped image, and an image where we applied random brightness. The raw collected dataset was biased, that is, the car was in a straight line for most of the time. Therefore, the data fed in batches was limited with constant number of steering angle 0 data. The images were selected at random among the three cameras along with the offsetted steering angle values for the left and the right cameras. This image shows the distribution of our dataset. As seen in the image, the x-axis represents the steering angles and the y-axis represents the number of images in thousands. As clearly seen from the image, the number of images having 0 steering angle are way more compared to the other angles. Overfitting was overcome by using L2 regularization and dropout layers. The model was trained using Keras on top of TensorFlow. Now let's look at the testing part. Since the Sonoma Raceway track is not a flat track in particular, we had to implement a cruise control plugin for the car to have a constant velocity. The car was tested on the track with cruise control switched on for the car and the steering angle of the car being predicted from the model. The model was able to take all turns properly and smoothly without any jerks or disturbances. We'll be seeing a video demonstration of the testing of the track later on in the results section. Now let's look at the second approach that we proposed in this project to solve the problem of autonomous driving, which is learning from own experiences using deep reinforcement learning. This is a more intuitive approach compared to the previously discussed deep learning approach, as here the car learns and decides the best action based on its own experiences rather than relying on the availability of good driving data. The environment used for this approach was the dirt track environment, as it was easier to define a reward scheme for this environment. We used the deep queue network algorithm proposed by DeepMind for making the car learn the best action to be taken from the current state in order to obtain maximum reward. DQN uses the queue learning algorithm, but a major difference being the inclusion of a deep neural network that acts as a function approximator to approximate the queue values, which are the state action pair values. While using a nonlinear deep neural network is powerful, training becomes unstable if we apply it naively. Thus, we need to make use of a couple of tricks. The first trick is using an experience replay. We need to store the agent's experience in a replay buffer and sample many batches from it to train the network. This decorrelates the data and leads to better data efficiency. Sometimes, before beginning the actual training process, the replay buffer is filled with random experience. The second trick is using a target network. That is, we use a separate network to estimate the TD target. The target network has the exact same architecture as a function approximator, but its parameters are frozen. After every certain time steps, the target network is updated by copying the parameters from the queue network to the target network. This leads to a stable training process as the target function is fixed. This approach was divided into three parts: training restrictions, data collection, model and training. Now let's look at each of them in detail. In order to simplify the problem, we reduce the action space of the car to only left, right, and do nothing. This is achieved by making use of the cruise control plugin written by us that fixes the forward velocity of the car to a certain value. Thus, now the only actions needed to be taken by the car are steering left, right, or do nothing and continue moving in the forward direction. The amount of left and right is handled by checking the previous action taken by the car. The steering angles have been defined in such a way that straight is 0 degrees, going right means we increase the steering angle value, and going left means we decrease the steering angle value. Now let me tell you how we adjust for the amount of left or right we want the car to move. So if the car is moving left or right for the first time, the steering angle is increased or decreased only by a small amount based on whether we are going right or left respectively. Next, if the left or right action is repeated by the car, we add or subtract a small amount to the current steering angle value, which is non-zero, based on whether the car is going right or left respectively. Thus, this way, we can easily handle the amount of left or right turn the car needs to make by adjusting the steering angle with a corresponding value. Examples can be seen in the table. As mentioned earlier, we use the trick of an experience replay where we store data prior to training and make use of this data during training to update our model. In order to do this, we added a small hack to decrease the training time. Instead of using the traditional approach of filling the replay buffer with an agent's experience collected by taking random actions, we filled the replay buffer with human driving experience. We first drove the car around in the environment manually and recorded the state, action, reward, next state, and a flag to check if the episode was over. This data was used to fill the replay buffer. The states in our case are the images obtained from the front camera mounted on the car. An example of the front camera image is shown in the figure. Now let's move to the model and training part. We used the same convolutional network that we used in the deep learning approach to act as a function approximator for the deep reinforcement learning approach. The input to this network were images coming from the front camera mounted on the car, and the output of the network were Q values. Unlike the deep learning approach, this was a classification problem and not a regression problem. However, we used the same model in order to achieve faster results by loading this model with the pre-trained weights obtained from the deep learning approach. This helps in faster convergence. For exploration, we use an initial epsilon of 1 and decay it exponentially over a fixed number of frames to a final value of 0.1. For training, we used a batch size of 128 and trained the model for about 1000 episodes. During each episode, the car selects the next action to be taken using an epsilon greedy policy, which basically means that the car will take a random action with probability epsilon and take the best possible action with probability 1 minus epsilon. Each Q value that we get as an output from the deep neural network corresponds to an action. The best action to be taken is the one that has the maximum Q value for the incoming image or current state. After each step, we store the current state, action taken, reward obtained, next state, and a flag that indicates the termination of an episode into the replay buffer. After each episode, we sample experiences from the replay buffer and train our network over those samples. The algorithm is shown in the image, which is taken from DeepMind's Human Level Control through Deep Reinforcement Learning paper. We finally move to the results part. This will be divided into two parts, one for the deep learning approach and one for the deep reinforcement learning approach. First, let's discuss the results obtained with the deep learning approach. After 60 epochs, the training was stopped as the loss reached 4 to 5% of the mean squared error plot, as it can be seen in the figure. The model was tested directly on the track. The video of the testing mode can be seen here. Now let's see the results of the deep reinforcement learning approach. As mentioned earlier, the training was carried out for a total of 1000 episodes. The training progress can be seen using the rewards graph shown in the figure. The training progress can also be seen in this video. Now let's discuss some of the possible future work that can be done by extending this problem further. As of now, we could only test the DQN algorithm. However, we had also implemented the deep deterministic policy gradient algorithm, which could be used with the same environment, but we didn't get enough time to experiment with it. DDPG is a result of combining three techniques together: deterministic policy gradient algorithms, actor critic methods, and deep Q networks. It is a policy gradient algorithm that uses a stochastic behavior for good exploration but estimates a deterministic target policy which is easier to learn. Generally, policy gradient algorithms utilize a form of policy iteration. That is, they evaluate the policy and then follow the policy gradient to maximize the performance. The actor critic algorithm is essentially a hybrid method to combine the policy gradient method with the value function method together. Actor corresponds to the policy function and critic corresponds to the value function. The actor produces the action for a given state of the environment, while the critic produces a signal that criticizes the actions made by the actor. Our future work would probably also include testing different reinforcement learning algorithms, as we now have a test bed which is ready and can be used to deploy and test the performance of different algorithms using the dirt track environment using ROS and Gazebo. Another possibility is to try applying reinforcement learning to the city simulation worlds with traffic and pedestrians. This would be very interesting to see. However, defining a reward scheme for such an environment will be a highly complex task. To conclude, we would say that we were able to achieve good results using both deep learning and reinforcement learning approaches. However, as it can be seen from the results, the reinforcement learning based approach seems to give a more natural driving pattern in scenarios that are not seen by the car. The car is also able to recover when it goes off track. Although deep learning is a very powerful tool, we can say that solving the problem of autonomous driving will not be possible by using deep learning alone. We need to use multiple technologies with a hybrid approach in order to solve the problem of self-driving. As of today, the problem stands far from being solved. Deep reinforcement learning can play a very important role in providing a more human-like driving pattern. However, this was a much simplified version of the real-world scenario. In the real-world scenario, we cannot define a reward structure and have the car learn from its mistakes by hitting into other cars, pedestrians, and property. A large section of the reinforcement learning domain still remains unexplored, and a lot more research needs to be done in order to be able to apply reinforcement learning in the real world scenario. Thank you so much. Please feel free to leave any comments, feedback, or suggestions that we could probably use to improve our work further.